Hello, everybody. My name is Reza Azerdiraksh. I'm CEO of PQSecure and also professor at Florida Atlantic University. So PQSecure is a US-based company focusing in post-quantum cryptographic hardware and software design. As you know, quantum computers are making progress, and we would like to develop solutions that are secure against the attacks coming from the quantum computers against the classical crypto that we use it today. So PQSecure is an information security cryptographic engineering company in South Florida. We come together in PQSecure to build new technology to address the cybersecurity problem from quantum things. And in this lightning talk, I will introduce you the challenges and opportunities of quantum safe migration, as well as the Silicon and IP for Chips Act. So quantum computers are, as you know, making great progress. Google, Microsoft, Amazon, IonQ, and a few other companies are making great progress in terms of building systems that can be useful for applications that we see today. These applications, as we see, I mean, they're very useful for various kind of problems that we can solve with classical computers. However, these algorithms are also capable of breaking our current security protocols that we use. For example, connection that we use in Team today, TLS 1.2 or even 1.3, if it's not migrated to post-quantum, using like classical elliptic curve Diffie-Hellman RSA kind of, or AES 128. And these algorithms, mostly the public key cryptographic systems and authentication systems, will be broken by quantum computers in polynomial time. So if we have cryptographically large enough quantum computers, for example, roughly about more than 2,000 logical qubits, these algorithms will be vulnerable. And with the attack, with the progress in building those reliable quantum computers, as we see today, it is predicted that by 2030 or 35 something, these algorithms will be unsafe to use. So there are a lot of activities happening in terms of the CHIPS Act, also quantum acts from the US government and all over the world, actually. And standardization came out for these algorithms, and also mandates, executive orders from the previous admin and also current admin about migration to PQC. So as you see, maybe DHS, DOD, DARPA, NIST, and NSF, various organizations are mandating industry and commercial technologies, also for DoD and non-DoD dual-use applications, to migrate to something which is called post-quantum cryptography. So post-quantum cryptography is something that we develop algorithms, classical algorithms, that could resist the attack coming from the quantum computers, which is, for example, the hard problems that we use today, for example, classical algorithms based on hard math problem for integer factorization, or discrete log problem over elliptic curves or integers. But NIST actually started this effort by 2018 and studied almost 80 algorithms submitted from all over the world for evaluation. And recently, last year, NIST came up with algorithms that you could see here. Key exchange and digital signature algorithms are two mainstream algorithms that we are worried about, and we need to migrate them. For example, Bitcoin is using them. We are using here blockchain technology, and everything that you are making a secure connection between your banks or IoT device going server. These are all using these key exchange and digital signatures for authentication. So MLChem is a modular lattice key exchange mechanism. It has its own document, FIPS 203 now by NIST. MLDSA is the digital signature. So these two algorithms are actually standardized, and the documents are out. And also SLHDSA, which is for another algorithm based on hash-based signatures for digital signatures. There are also some upcoming algorithms by NIST actually happening for key exchange and digital signature, and they'll be very out soon, actually. HQC, which is code-based for key exchange again, and FNDSA, which is another digital signature based on, again, lattices, will be available. So with these algorithms in place, still we are not confident of having covering all solutions and needs that we need for devices, for example, IoTs, small devices, autonomous networks, car-to-car communications, or even satellite kind of solutions, medical devices, and other things, right? So some algorithms got also endorsed by NSA, under CNSA, commercial national security algorithms, and only MLChem and MLDSA chosen from NIST algorithms. So SLHDSA, HQC, FNDSA, they're not there. On the right side, because these algorithms are not covering every kind of applications, still NIST is studying better digital signature algorithms, because these digital signature algorithms are a lot bigger. I'll have in the few slides coming up, I'll show you the sizes that are very big in comparison to classical cryptography. So CNSA, NIST is actually algorithms on RAP, evaluating some algorithms with the hope that these will be standardized maybe in the next 5 years. CNSA recommended only MLChem and MLDSA level 5 security, for example, 1024 and 87, symmetric key cryptography, AES, SHA-2 and 3, and for some applications that we need to do firmware update, software signing, code signing, like XMSS, LMS, these are also stateful hash-based digital signatures. So so standardization is out, documents are ready, recommendations have been made, and mandates coming from government. So we are looking into fast followers and fast movers, actually, or first movers. With that, as you could see, energy, utility, manufacturing, DoD, I think you've seen that the mandates coming from recommendation from DHS for even OT networks, for infrastructure, security, banking, financial. ISI SAC is also considering financial, telecommunications, aerospace, and defense for satellite communications and transportations are the ones that are looking into that, and mostly they are considering deployment of crypto algorithms like before in hardware, well, starting with software and then moving into hardware. So the question is that if we have devices that we would like to make them quantum safe, secure communications, how you are going to deploy PQC into the device. So there are various ways, starting with software, as DHS is recommending to start with. Reference codes are given by NIST and studied by globally. ANSI is the standard model, device level optimized, assembly available, C to Rust implementations. You know that Rust is another challenging for software implementation because of memory vulnerabilities that we have from C. And also side channel protection and formal verifications are, as you see, pushing these days, because a lot of vulnerabilities are being added into C programming. On the other side, you see that we have, for example, hardware implementations that are, when it goes to silicon, actually every single IoT device that we use today, edge device, they're implementing classical crypto in hardware. And that's important because it gives you side channel protection, and also it gives you power energy consumption efficiency. So these could be FPGA or ASIC implementations with assurance and also protection against side channels. Hardware software co-design is something also the White House recommended for agility, what they call hardware software co-design for PQC, because these algorithms are replacing classical algorithms, and we would like to have them somehow working for a while as a crypto, I think, solutions. We need to be aware of the legacy systems and being able to work with them and addressing the needs of classical cryptography. So agility is a big thing. I think is a lot of people talking about. NIST had an agility conference. In terms of implementations, compliance, security strength, what security level you would like to use. CNSA is recommending only level 5. Google Chrome, for example, Google search currently is using level 3 security for MLChem, as you see. You can see check from your browser. Migration, retirement, how to turn off ECC, RSA, and they stay with PQC, composability, platform, and context. If you're implementing in hardware or software, but vulnerabilities, or even if you're implementing PQC in a software in an unreliable hardware, that's also challenging. So a lot of these questions need to be answered, and at PQC Secure, we are happy that we are working on them. So cryptography is important in terms of, as people are doing software libraries, dedicated hardware instructions, the trust platform, TPMs, HSMs, you know, security enclaves. Small single iPhone is using several of these HSMs and TPM, as you know. So when it comes to folks, I think implementing or performing or doing cryptographic engineering, some people say I can't do it. Some people they say we can. Some companies actually we can do it for me or give me some start point to start with it. PQC, unfortunately, is very challenging in comparison to classical cryptography because of lack of resources in terms of a talent in the country, and it's a challenging thing to find people that they have right skills to implement this securely. So software side is very challenging, let alone hardware is a lot more challenging than it. So I have listed here this figure, as you could see. We start with these algorithms, performing risk assessments, exploring PQC algorithms. Which one of those algorithms that I showed you, for example, 3 are already standardized, 2 are upcoming, 10 more under investigation. Some of them are already recommended by NSA. And these are giving customers, I think, people that they would like to migrate or deploy them, a little bit of confusion in terms of the application. So we offer studying algorithms for users, for your devices, for platforms, for your cloud, and study how to implement them in software or hardware, how to make them secure against the attack coming from physical access, for example, physically fault injection attacks or side channel attacks, power emission, timing attacks that could be very vulnerable into your device, and also focusing into deployment into target performance, because sometimes performance or that you'd like, for example, it's a time-sensitive network or medical devices or even some IoTs in special fields that they need the real-time response and decision making. So we can add extra latency here. So for, as you could see on the here, FIPS 140-3 requirements are looking for implementing these algorithms securely against fault injection and as well as the non-invasive attacks like power analysis or timing analysis attacks. So, and then also perform study in terms of assurance for the device implementation to make sure that they are actually implementing formally verified. So I listed here a little bit of techniques of side channel attacks. Could be fault injection attacks, could be AI assisted profiling attacks. AI is very helpful for attackers here because they can perform sometimes single trace attack on software implementations and the power analysis attacks and many other DPA, CPA, and many others. So this is something that people need to be aware of. Implementing securely PQC algorithms is very challenging, and this needs to be addressed. So in software, basically, because you're running your software sequentially all the time in your MCU or microcontroller or microprocessor over there, there are a lot of attack mechanisms when you're implementing in software, and that's why people usually look into hardware implementation. So I compared here a little bit of these algorithms. As you could see, for example, MLChem key sizes. For example, if we are talking about classical crypto of ECC, we are talking about 32 bytes, but here we are talking about MLChem, which is something like a 1.5 kilobyte, right? On the right side, as you could see, digital signatures. If we're comparing ECC, which is 64 byte of ECC, MLDSA, which is the mainstream of implementations, the size goes up to 7.8 kilo, the purple size on the right side, as you could see. FNDSA, for example, on the other side is very more efficient, but it has its own challenges of being hard to implement floating point arithmetic in hardware. And Sphinx, which is SLHDSA, is offering a lot more, I think, signature sizes, 29 kilobyte, which is kind of infeasible for IoT devices. Some folks are talking that, hey, classical crypto, I mean, PQC, Kyber, for example, MLChem is faster than ECC, but that's not actually true, because if you implement securely, as you could see on the none, we don't have side channel protection mechanism for Kyber, and that's like something like similar to ECC. If you're adding first order masking into Kyber or MLDSA, it becomes 3 times faster. If you add second order, it becomes like tens of times faster, and if you do third order masking, still it gets broken and it's not secure. 49 times slower than classical cryptography, which means in software performing crypto PQC is very challenging, and that's why we are here. We are offering PQC solutions that are implemented in hardware basically offering AES-256, ASCON, inline memory encryption, SHA-2/3 for all kind of applications, SHA-2 mainly for CNSA, LMS, XMSS, Crystal, Kyber, Dilithium, and Sphinx or SLHDSA. And on the other right side that you could see, we have various offerings of these algorithms. They're all NIST certified based on CAVP and also CNSA kind of compatibility for implementations. We have TRNG and Trivium for pseudo random number generation as well. So the task of addressing the agility in hardware is becoming very challenging, because sometimes if you'd like to go do everything in classical crypto like what we do, put everything pure hardware, it becomes less scalable. It is great actually for swap size, weight and power applications. It's very fast, very efficient. You're offloading everything from CPU. For example, for HSM applications, your CPU is already busy dealing with a very other transactions than they would like to perform crypto things in hardware. So and it's also low power or low energy. But the fact that it's not basically agile, or you can upgrade or address various security levels. So we offer solutions that are computational intensive parts to silicon IPs. For example, it goes to an FPGA or ASIC. For example, AES, SHA-3, vector arithmetic, Boolean arithmetic over there. And then we keep high-level computational things in software. Could be a MCU in a CPU or RISC-V technology. It gives you scalability, flexibility, over-the-air updates that you want to do. All devices that we use these days mostly are becoming compatible of over-the-air updates, and extra and utilization for host also a little bit you get from software implementation. So PQSecure is designing solutions based on hardware, software co-design, system on chip, algorithm primitives, minimizing performance solutions and maximizing the agility as much as possible, with in mind having also side channel protection, which is very tricky and challenging when you are implementing them in software. So here we have our portfolio. We have more than 30 patents filed for and granted actually for PQC implementations in hardware, SHA-2, SHA-3, ASCON, XMSS, LMS, and side channel DPA protections, various techniques that we use for maxing, efficient masking, because masking by itself adds a lot of I think overhead into the solution. So here we have a MPS2 plus the FPGA device. Here we are developing actually software and hardware co-design. We work with various companies. As you can see, we're partner of Microchip, AMD, Intel, Altera, Lattice, and as well as the ARM. We are ARM Flexible Access Program member. We have access to ARM IPs, and we can actually perform hardware, software, or pure software in ARM processors and IPs into any FPGA, ARM and Intel, Xilinx, AMD, and others. And also we are RISC-V member. We have developed hardware software solutions, purely software implementations in RISC-V, as well as hardware software co-design controlled by RISC-V. So which makes it agile in terms of the fact that you would like to have an open source hardware. So I have a comparison here for one of the mainstream algorithms for PQC, for example, Kyber and Dilithium. As you could see on the left side, I have ARM Cortex M4 implementations. Cortex M4 is in smart glasses, smart watches, smart Fitbit. They're using this M4 hand optimized C assembly implementations. As you could see here, we are comparing unprotected and protected. Unprotected means it's not secure against side channel attacks. And as you could see, both hardware and software, as you could see here. So pure hardware implementations could be 78 times, 120 times faster than software implementations. And if you are adding protection into your hardware, it will be still 16 to 25 times faster than your software implementations, which is actually great. We're comparing actually here fairly with hand optimized ARM Cortex M4. It says assembly. It's not C. If you implement comparing in C, maybe it's going to be 500 times faster than, or several hundred times faster than software implementation. So on the right side, I have Dilithium is MLDSA. hardware implementations or silicon implementations. These are implemented in ARM, RTX 7 FPGA, as you could see. PQSecure hardware implementations could be 40 to 177 times, because keygen and sign-on verification, they're different. Verification doesn't need protection, you know. And also side channel protected ones could be 71 to 31 times faster. So if your device is performing into small devices and you want to have protections here, I think that's the beauty of hardware offering it. So PQSecure is working on with also third-party companies. We have Rescure currently, actually recently they acquired by Keysight. We had the government prime contractor. They would like to have a third party to look into our IPs, because there is no NIST standardization and evaluation methodology, NIST labs for side channel and I think evaluation. We provided all of our IPs encrypted and open source to them. I mean, without encryption, functional testing against CATS, non-answer tests, and pre-silicon leakage analysis, security against all vulnerabilities, and we're happy we can share these results with the customers if they would like. We also work with one of the Ementa is a open source, you know, that agile embedded FPGA. They evaluated our IPs into their own embedded FPGAs. We have a design here, as you could see, implementing both Kyber and Dilithium, MLChem and MLDSA, FIPS 203 and 204, completely with side channel protections. Those graphs that you see on the left and right of the algorithm, they are actually real from TVLAs, test vector leakage analysis, and they show that no leaks here, because they're between the required thresholds, and also secure against fault injection attacks based on FIPS 140-3. And as you could see here, we have also silicon usage occupied number of LUTs. For example, it goes about 13 kilo LUT for full complete implementations of MLChem DSA together. With full conservative side channel protection. For example, it goes to keygen, sign, keygen for Kyber, and as well as the decryption or decapsulation algorithm. So here is our setup. We have, as you could see, we're using some chip whisperer tools as well as our own Phobos. We collaborated with GMU. We developed our tools for here, as you could see, implementations that go here. For in FPGA, we get power traces, and then we have a PQScope go to computer. We get the traces, power traces, consumption, power traces availability that we compare against the statistically probability of the I think leaks against those threshold values defined by the TVLA or ISO standard or FIPS 140-3. So on the right side, we have also software platform here. As you can see, is an ARM Cortex M4. We perform software and then we do leakage analysis for software. So this is one of our successful side channel attacks against one of the well-known Calyptra. You may know, you might be familiar with Calyptra. Is a open source consortium implementing HSM kind of solutions for very high performance implementations. And recently they upgraded to MLDSA, PQC's digital signature. We were able to actually unprotected MLDSA here. We were able to break it, and we had a demonstration at a host conference. This Calyptra composed of companies like Google, AMD, Microsoft, and NVIDIA. And we provided them with guidance how to get into making it more secure or add side channel protections that hopefully they're going to add it into Calyptra 2, which is actually what we did here. It was a side channel based on correlation power analysis attack. Very successful. We were able to cover the secrets. So our solutions and IPs that, as you could see here, also we have CAVP program certified by NIST. You can go to NIST certification program. You search our company's name over there, and then you'll be able to see our hardware implementations, our software implementations, as well as our hardware software co-design implementations. And also even we have recently coming up our Rust implementations. for cases that you want to do software, but you're worried about your software memory vulnerabilities, and because of government mandates of Rust, you know, the Tractor program transfer all C to Rust program to, for example, secure memory secure or memory safe languages. So this is actually available now. Our IPs, Silicon crypto IPs, are available in various performance and security levels. We have 4 performance levels, for example, tiny, compact, medium or balanced, and very high performance for cloud and server applications. And we have also covering all security levels, level 1, 3.5 for MLChem or SLHDSA, and also 2.3.5 for MLDSA for digital signatures, and for also other XMSS, LMS, FNDSA, and I know they are not standardized yet, they're upcoming, but still we do have IPs for them. But mainstream, which is also recommended by CNSA 2.0, we are silicon ready, we are ready to use as of today. So I would like to stop here. I think my time is finishing, and I would take if there are any questions. Thank you very much, everybody.
Thank you. Thank you, Reza. Just monitoring the Q&A and chat, so feel free to ask questions. We have probably time for 1 or 2 questions here. I'll go ahead and ask one question that it's in my mind is,
Yes.
If we, you know, a lot of folks here and probably in the market who already have IP in place. So whether it's hardware and software, are there any integrated tools that can sort of tell you what the vulnerability is there to the IP and what you can do with the current IP in order to make it compliant, if you will?
Sure. So we perform, okay, if you have already classical crypto, of course you need to get rid of classical crypto, or you have it classical crypto working with PQC algorithms, right? For example, if you already have ECC or RSA, you need to somehow use PQC with it. And if it has side channel protections in it, great. If you need to go to TLS 1.3, definitely you need to have some upgrades and updates. If you would like to have address the 140-3 and ISO for the side channel protection, fault injection, attacks protections, you need to upgrade them from classical to PQC, or even higher level securities of classical crypto. So we also do red teaming. We analyze, investigate, we perform security leakage analysis and testing on various PQC algorithms or even classical crypto. We have been working with ARM via the ARM Flexible Access Program. We have been doing this for ARM. We wanted to upgrade the classical algorithm to PQC, and that's what we are offering already. So we do crypto discovery in your devices or your systems that you have, and then we recommend how you are going to address the needs. If you want to use, for example, already you have a device that it has a SHA-3 engine there, then we can work with it. We can add a little bit more if there is availability of FPGAs or embedded FPGAs there. You don't need to go ASIC. We can do everything in FPGA and integrate our, for example, MLChem DSA solutions using your own available SHA-3 engine there, for example, doing the MLChem DSA. Or if you want to do NSA recommended algorithms, LMS and XMSS, we can still use your own legacy SHA-2 if it's protected, much better. If not, we can provide guidance to protected it and then using it for like SLH DSA or XMSS LMS.
All right, thank you. And if you folks are monitoring the chat line, there's also one of the attendees posted a funding opportunity there that you could take advantage of. I want to thank our first speaker, Dr. Reza Azar-Tarakesh, and for a fascinating discussion. If you have any questions, obviously you can reach out to him directly, and as well as letting us know, and we will pass on that question to him.